Okay, this next section is called quantization, uh, Planck, Einstein, energy, and photons. And so this is can be a little bit of a long section, but we're going to give it a go. So the goals are to understand the photoelectric effect and to understand that the energy of a photon, a massless particle of radiation, is proportional to its frequency. So I have here, go to page 281. And let's see what I have here on page 281 that I wanted to show you. Oh, I see it. Well, I'm going to skip that for right now. So quantization, and I believe that's the correct, well, they call it quantization, so they get rid of this, quantization. Let's take a look at what we call, or what I've been told is black body radiation from the past. This is when you take an object and you heat it, like a iron. So let's say you have a branding iron and it's rather dark in color, right? When you put it in the fire, you'll notice that it starts to get warm, and then eventually it starts to glow red. And then the hotter and hotter it gets, it actually starts to glow white. So why is that the case? Well, here we have what's called a graph that shows the wavelength that the branding iron is emitting versus the, if you will, the intensity of the light. Okay. So when the branding iron is first heated up, you can see that what happens here is that you get a lot of energy being released, or wavelength being released here in this region here that goes from about 400 to 650 nanometers. Now remember, this is VIB-GYOR. So that means that if you have a lot of intensity here around the red, that branding iron is going to look red. Now, what happens when you heat it up even more? When you heat it up even more, what happens is the intensity of the wavelengths increase, shifting more towards the lower wavelengths, okay? And here, when it shifts, so we're looking at the blue line here, you're looking at all sorts of wavelengths being released, and all of those wavelengths of visible light together will look like white light. And when you heat it up more, you have all of this being given off, and so you have this really intense white light. So these figures in blue show what you actually see experimentally for the intensity versus the wavelength. And you can see that the intensity drops off eventually for each one of these. Now, this blue is experimental. This is what we actually find for the intensity versus the wavelength. Theoretically, what we expect is that, well, for a lower wavelength, we should have more energy. And so the graph should look like the green. And the question is, well, why doesn't it look like the green? And the solution was came from a guy named Planck, who said basically that the atoms vibrating are your source of light. And when the atoms oscillate around a certain position, they give off energy. And it turns out that there is a range of oscillation. You can have a few oscillating very small, giving off very little energy, a whole bunch oscillating a lot, giving off a lot of energy, and then a very few oscillating just like gangbusters, but giving off very little energy. So here the oscillations would be great, but there's only a few of them doing it. And so eventually what's going to happen is you heat up the atoms, more and more of them will oscillate faster, but you never get them to oscillate completely, so that the ones that are oscillating the most are the largest population. Okay, so this all came about because the oscillations were supposedly quantized, which means you can only have certain oscillations. You can't have in a continuous amount of oscillations. So when we talk about quantized, the best way to describe it is that you can have oscillations that are stepwise. You can have them here, 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 or here, but not a ramp of oscillations. So it's kind of like the steps versus a ramp. Here at the steps, you can only be a certain height above the ground. Here with a ramp, you could be technically at any height above the ground, an infinite number of spaces. So what do we get out of this? We've got something called Planck's equation or Planck's equation. I'm not sure how to pronounce the name. And basically you get that the energy is equal to h nu, where this is Planck's constant and this is frequency. We can rewrite this as the energy is equal to hc over lambda, and Planck's constant is this value here, 6.626 times 10 to the minus 34 joule seconds. Okay, we'll be using that equation in a little bit. That's something you want to plug into your head, and we'll be using it soon. Now let's look at the photoelectric effect. So right now, I want you to imagine going back here, we're looking at treating light as waves. And the photoelectric effect tells us that, well, maybe we shouldn't treat light as waves. So let's take a look at this photocell here. So this little thing that looks like I don't know, I want to call it like one of those globes that you shake up and snow comes flying down like a snow globe. So here, if you take a look at this, this is a photocell. And in this photocell, you have these two pieces here. This guy, which is positively charged, called the anode, and this, which is negatively charged, called the cathode. I never did like these names because anode to me is like anion and cathode is like cation. So why is the negatively charged piece called the cathode? And the answer is because it attracts cations to it. So the anode, why is it called the anode and why is it positively charged? Because it attracts anions to it. So this photocell, the cathode is made out of a metal, and different metals will react differently. But what we see in this picture here is a wavelength, if you will, of light that is hitting the cathode. Now the frequency here is kind of how do I want to say this? It's not high frequency, it's low frequency. There's not many waves passing per minute. Okay, so we're talking about low frequency light, and it hits the cathode and nothing happens. Now, if something did happen, what would happen is an electron would be knocked off the cathode, and the electron, because it's negatively charged, would be attracted to the anode. It would go through our meter and come back here to the cathode and be ready to be knocked off again. And the more electrons you have per minute, the higher the current. So what we have here is a graph of current versus frequency. So here, with my arrow, we're showing that over to the right is high frequency and over to the left is low frequency. So here at this low frequency, which is also low energy, remember E equals H nu. At low frequency, we have low energy and there's not enough energy to knock the electron off. Now that's kind of contrary to what we actually expect. What we kind of expect is something down here. At low frequency, you expect to have very few electrons knocked off. But as you increase the energy, you would be increasing, or the frequency, you'd be increasing the energy, and therefore you'd expect to have more electrons being knocked off, okay? That's what you expect. But the interesting thing here is at a low frequency, you basically get no current, no electrons are being knocked off. And then all of a sudden, boom, when you reach a minimum frequency, an electron gets knocked off. So this is higher frequency light than this low frequency. Okay, now what happens if we increase the frequency of the light? So here you can see I've tried to make it look like more waves pass per second here in this one. So what if we had this happen where it's a really, really, really high frequency and it hit this cathode? And the answer is still one electron would be knocked off. So really high frequency light knocks off one electron and causes current. So you reach a minimum amount of energy and an electron gets knocked off, but only one or two or 20, whatever. When you increase the frequency, more energy, you get the same number of electrons knocked off per second. So how is it that this really high energy light and this lower energy light give the same current, that is, give the same number of electrons knocked off per second? We don't know. We need to figure that out. Now here, imagine instead of having just one high frequency light, we have two. So here, this might be a light bulb of a certain frequency hitting the cathode. What if we had two of those light bulbs hitting the cathode? Well, you'd get twice as many electrons knocked off per second, so your current would double. So again, for all of this, we kind of expect this to be the trend, not this weird curve where it's flat, then it rises dramatically, and then it flattens out again. So what's going on here? So this kind of summarizes this. You have to have a minimum frequency required to cause a current, so a minimum amount of energy. The current depends on the intensity and not the frequency once the minimum frequency is reached, and zero current if the frequency is too low. So treating light as a wave doesn't really explain this occurrence or this experimental data that we collect. So what's going on here? Well, there's a person named Einstein who came up with an explanation for the photoelectric effect. So let's take a look again. This is what we expect. This is what we get actual for the current versus the energy. So Einstein said we can model electromagnetic radiation as packets of energy called photons, and the photons are massless. So we're going to treat energy not as waves, but we're going to treat it as little packets of energy, photons. So here I have a weak photon. You can see how small the dot is. Here I have a stronger photon. You can see how big the dot is. And here I have a really strong photon. You can see how strong the dot is. Now the idea is pretty simple, that one photon can knock off one electron and that's it. But the photon can only knock off an electron if the photon has enough energy to do so. So if you go to the county fair and you see the game where they have little cats on swivels where you throw a ball and you try and knock a cat down. They're not real cats, mind you, they're just little fake cats. But you knock the cat down, and if you knock 3 cats down, you win a prize. So you're throwing these softballs at these cats that'll bend over, if you will, and knock down if you hit them. So 3 balls, you knock down 3 cats, you win the prize. Now, what happens when you hit a cat? How many cats can you knock down with 1 ball? Well, once your ball hits the cat down, it can't bounce back out and hit the cat again or hit another cat. So you knock down 1 cat per ball. So what happens if the ball and its speed is the strength of the ball? So it turns out that if you throw the ball very weakly, you might not be able to knock the cat down because those cats are kind of stuck there. So here, a weak photon, a weak ball would not knock a cat down, so you get no flow of electricity. Now, what happens if you have a person who can throw the ball a little harder and they hit the cat? Well, they can knock the cat down and you get the flow of electricity. So what happens if you have a professional baseball player throw the ball? Well, turns out that 1 ball still can only knock down 1 cat or release 1 electron. And of course, to knock down 2 cats, to get 2 electrons, you have to throw 2 balls. So that's the idea here, is that you must have a minimum amount of energy to knock the cat down. And once you reach that minimum amount, you're still only going to knock 1 cat off. So how do you get twice the current? You have to throw twice as many photons to get that done. So this is a great explanation for the photoelectric effect and why we see what we do. So now we have 2 models of light. One model is the wave model, and the other model is the photon model. So which model is correct? And the answer is whichever one is going to give us the best predictions for what's going to happen. One of the things we have to understand in chemistry and in all fields is that models are called models because they're not the real thing. So if they're not the real thing, they will never be as good as the real thing or be able to fully explain the real thing. So what's the best we expect out of a model? And the answer is we expect the model to make some decent predictions about the behavior of natural phenomena. And if it doesn't make decent predictions, you get rid of the model or you try to refine the model so it makes better predictions. So here we have 2 models, a wave, not a perfect model, And we have another model, the photon, not a perfect model. Okay, so when we go to this quantization, so again, I'm putting in this extra part here. When we go to quantization for the photoelectric effect, turns out that we don't need a different equation than Planck's equation. We can still use that. However, this morphs into this, that the energy is the energy of one photon. Okay, so that's how it changes a little bit for the photon model, is that the energy we're calculating is the energy of one photon. It's kind of nice that we still get to use the same equation. So let's take a look at some problems using Planck's equation and the photoelectric effect. So here we have energy and chemistry using Planck's equation. DVD players are lasers that emit red light with a wavelength of 640 nanometers. So I'm going to put the wavelength is 640 nanometers. What is the energy of one photon of this light? Well, the energy of one photon is equal to lambda nu, which is also equal to let's see, we have this in terms of wavelength and frequency. Oh, I've got the wrong equation here. That C is equal to lambda nu. I need H nu, okay? Now here we don't have the wavelength. What we actually have, or we don't have the frequency, we have the wavelength. So we've got to change this to this nu is equal to C over lambda. So if I substitute this in for that, I get HC over lambda. So Planck's constant is 6.626 times 10 to the minus 34 joule seconds. The speed of light is 2.998 times 10 to the 8th meters per second. And lambda in this case is 640 times 10 to the minus 9 meters. Now the energy is going to come out to hopefully be joules. Let's see if the units work out that way. So can we see how this second here is going to cancel with that second there? This meter is going to cancel with this meter. And so what do we have left over? We have joules left over. So here you can see that 10 to the minus 34 times 10 to the 8th is going to be what? 10 to the minus 26. When you bring this up, it comes 10 to the positive 9. So negative 26 and 9 brings us down to what? 10 to the minus 17? Okay, and then we have these three to contend with, which is going to make things a little more interesting. Well, we know the value is going to be around 10 to the minus 17-ish, probably a little bit different than that, maybe 10 to the minus 19. So let's take a look at these values here. 6.626 second EE negative 34 times 2.998 second EE8 and divided by 640 second EE negative 9. And let's see what we get. Equals 3.1 times 10 to the minus 19 joules. Minus 19 joules. And I'm going to leave it at two significant figures because 640 only has two significant figures. So this is the energy of one photon. So what is the energy of 1 mole of photons of red light? Well, the energy of 1 mole is going to equal 3.1 times 10 to the minus 19 joules. And I'm going to put 1 photon here. Okay. And then I'm going to multiply by, let's see, there's a 6.022 times 10 to the 23rd photons per 1 mole of photons. And we'll get the following answer. So times 6.022 second EE23, and I get one. Wow, I get a big number. 2 zig figs, so I get 1,900,000 joules per 1 mole of photons. Probably a better way to write this would be in scientific notation. So I'm going to set my calculator to do that for me. And I get 1.9 times 10 to the 5 joules per mole. Okay, so one of the things I'm going to warn you about, I don't know if we have a problem that looks like this, but if you're given the energy for 1 mole, so let's say you're given that, you cannot calculate the wavelength directly or the frequency directly. So here you cannot calculate the wavelength, you cannot calculate the frequency, even though E equals M or H nu. The reason you can't do this directly is because this is the energy of 1, not 1 mole. So if you're given this, what do you have to do to be able to calculate the wavelength or frequency? First thing you have to do is change that into the energy of 1 and then calculate the wavelength and the frequency. Okay, so remember to do that. All right, let's take a look at another problem. So here we have actually 3 more problems. Electromagnetic radiation and Planck's constant. Green light has a wavelength of 5.00 times 10 squared nanometers. What is the energy in joules of 1 photon of green light? So the energy of 1 photon is equal to h nu, which is also hc over lambda. And here we're going to plug in 6.626 times 10 to the minus 34 joule seconds. That's Planck's constant. Speed of light is 2.998 times 10 to the 8th meters per second. And then lambda, we have 5.00 times 10 squared times 10 to the minus 9 meters, because that nano means 10 to the minus 9. So here, if I kind of clean this up, this is going to be 10 to the minus 7, and I'll cross those out. And we put this into our calculator. Okay, so 6.626 second EE negative 34 times 2.998 second EE 8, and then divided by 5.00 second EE negative 7. And I get 3 significant figures because of that. 3.97 times 10 to the minus 19 joules, and that's per photon. So what is the energy of 1 mole of photons? The energy of 1 mole is going to be this 3.97 times 10 to the minus 19 joules per 1 photon times 6.022 times 10 to the 23rd photons per 1 mole. So I take this number and multiply by 6.022 second EE 23. And we get 2.39 times 10 to the 5th joules per 1 mole. Okay, so that's that problem. Let's look at this next problem. The most prominent line in the emission spectrum of aluminum is at 396.15 nanometers. What is the frequency of this line? So we have E is equal to H nu. And here, We also have C is equal to lambda nu. So which equation do we want to use to figure out the frequency of this line? Because we have frequencies here and here. Well, what do we know about this? We know the wavelength, so there we go. Do we know the energy of this line? We don't. Do we know the speed of this line? We do, 2.998. So I'm going to use this equation here to solve for the frequency of the line. So the frequency is equal to C over lambda, and that's going to be 2.998 times 10 to the 8th meters per second, all over 396.15 times 10 to the minus 9 meters. Okay, so the meters will cancel. The second doesn't cancel, but the second is in the denominator, so that's where it stays. So 2.998 second EE8 divided by 396.15 second EE negative 9. So this negative 9, when I put it in the numerator, becomes positive 9. So that's going to become positive 17 in the top. And here, when I have this divided into that, that's going to be like 0.001 or something like that. So things will shake up and I'll end up probably with around 10 to the 15 or something like that. So let's see what we get. And we got close to 10 to the 15. We got 7.568 times 10 to the 14 per second. Now, you may think this is odd. How is it that we don't have a unit in the numerator? And the answer is because frequency is per second. The unit belongs in the bottom. And that's it. Okay. So what is the energy of one photon with this wavelength? Now we're going to use this. So the energy of one photon is going to be equal to, let's see, how do you want to do this? Do you want to do h nu? I think we'll do h nu since we just figured out what nu is. So 6.626 times 10 to the minus 34 joule seconds. And then we have times 7.568 times 10 to the 14 per second. You can see that the seconds cancel. 6.626 second EE negative 34. And so here I get 5.014 times 10 to the minus 19 joules. So that's the second part. And then what is the energy of 1 mole of these photons? Well, we take this energy of 1 mole is going to be 5.014 times 10 to the minus 19 joules per 1 photon times 6.022 times 10 to the 23rd photons per 1 mole of photons. So I'm going to take this number I just got and multiply by 6.022 second E23, and we get 3.020 times 10 to the 5 joules per mole. So here you'll notice I have 4 significant figures here, 4 here. I have 4 here because when we take a look at all these numbers we use, this has 4 zig figs, this has 5. So I get 4 here. Here this has 4, this has 4, so we get 4 here. This has 4, this has 4, so we get 4 there. Okay. So let's take a look at this last one here. Place the following types of radiation in order of increasing energy per photon. Okay, so we have yellow light from a sodium lamp. So A is visible light. B, we have X-rays. C, we have microwaves. And D, we have radio waves. So if we go back and look at the chart, we have gamma rays, and this is high energy, which is also high frequency. And then we have X-rays, and then we have ultraviolet, and then visible, and then infrared, and then microwaves, and then radio waves. And so this is low energy and low frequency. Now, the reverse is true for wavelength, since they're inversely proportional. If this is high frequency, this is short wavelength. And if this is low frequency, this is long wavelength. Okay, so our job is to place the following in order of increasing energy per photon. So it turns out we can use this chart to calculate the energy per photon. And increasing energy means this. So increasing energy. So we want to put high energy here on the right and low energy on the left. So out of all of these, the lowest energy is going to be the radio. So that's going to be less energy than microwave. And that's going to be less energy than visible. And that's going to be less energy than X-rays. And most of this we could have done intuitively, right? None of us are afraid of radio waves. We're not afraid, oh my goodness, I'm going to get cancer from radio waves or something like that. We are very afraid of X-rays, so you know that's going to be high energy. And you know radio waves are going to be low energy. What about visible waves? Are we really afraid of those? And the answer is not really. What about microwaves? Well, yeah, you don't want to get into a microwave oven. So these are the only two that you might have confusion with, because it turns out that microwaves indeed have less energy than visible waves. So why is it that microwaves are used for cooking and visible waves aren't? And the answer is, well, you can use visible waves for cooking, but you'd have to have high intensity visible waves. It's a lot easier for us to get these high intensity microwaves. All right, so that's that one. Okay, let's see now. Let's put that off to the side. And we have another problem here. This will be the last one for this section, the photoelectric effect. An energy of 3.3 times 10 to the minus 19 joules per atom is required to cause a cesium atom on a metal surface to lose an electron. So what we're talking about is a photon striking a anode, and it releases an electron, which goes to your cathode, because electrons are negatively charged and cathode or anodes are positively charged. So anode, cathode. I probably said that incorrectly. I always get confused by this because of the opposite, if you will. So the photon strikes the cathode. This is weird for me to draw a photon like this because photons have no mass. They're not particles. It's a packet of energy. But I don't know how to draw a packet. I mean, is this like a packet of a sauce that you put on something? I don't know. So here, you got to imagine, even though I draw this as a dot, it has no mass. The convention, though, is you just draw a little circle and that's a photon. Some people even put little flames coming from it. I don't know where that comes from. Okay, so at any rate, here's our massless packet of energy hitting the cathode and striking an electron from it. The energy of this photon is 3.3 times 10 to the minus 19 joules. And when they say joules per atom, what they're really saying is that this is the one photon striking one atom and knocking one electron off, okay? So we could say that this is 3.3 times 10 to the minus 19 joules per photon. It's 3.3 times 10 to the minus 19 joules per atom or per electron knocked off. Okay, now this says this is the energy required to remove the electron. Calculate the longest possible wavelength of light that can ionize a cesium atom. So remember, we got a cesium atom here, and it's just lost an electron, and that cesium atom has become a cesium cation, okay? And that electron's eventually going to come back and turn that cesium cation back into a cesium atom. Okay, so what does this mean? The longest possible wavelength. Longest possible wavelength. Well, we need to remember that the relationship between wavelength and energy is as follows. Hc over lambda. So this means for the longest wavelength, we're looking for the lowest energy. So when we talk about the longest wavelength, what is the lowest energy that will ionize this cesium atom? Okay, so when they say this is required, that's the minimum energy required, all right? So we want to find the longest possible wavelength. We know that energy is hc over nu, so that means wavelength is equal to hc over energy. Okay, so I think we have all that we need to be able to do this. H is 6.626 times 10 to the minus 34 joules seconds. Notice I'm not saying joules per second, because per second means over second. So when I say joule second, they're both in the numerator like that. And again, that's kind of weird for us to see 2 units in the numerator like that. And we got 2.998 times 10 to the 8th meters per second. You can see that these seconds are going to cancel. And then the energy is 3.3 times 10 to the minus 19 joules. Okay, so let's calculate the wavelength here. You can see that the joules cancel, and we're going to be left with meters here. Okay, so let's see what we get. 6.626 second EE negative 34 times 2.998 second EE8 divided by 3.3 second EE, oops, I messed that up. Second EE negative 19. Hopefully that works itself out. And I get 6.0 times 10 to the minus 7 meters. Okay, so now we're asked, what region of the electromagnetic spectrum is this radiation found? So I'm going to move this up here, and I'm going to show you how you can deal with this. Now, when we look at the electromagnetic spectrum, we've got gamma rays, we've got X-rays, we've got ultraviolet, we've got visible, we've got infrared, we've got microwaves, and we have radio waves. Now, which part of this spectrum do we know? And I'm going to fill something else in here. This is going to be high energy frequency, and this is going to be low energy frequency, which means this is going to be short wavelength, and this is going to be long wavelength. So I want to fill all those parts in because I'm going to put visible light in here. Now, visible light is the only type of light where I want you to know the wavelength. So what is the short wavelength for visible light? It's around 400 nanometers. And depending on the book you look at, you would say that the long wavelength visible light is either 650 or 700 nanometers. I'm just going to put 700 nanometers because we have a nice range there that goes 300. So short wavelength, long wavelength. So where does this fit into that? Well, let me show you a way to convert this to nanometers. 6.0 times 10 to the minus 7 meters times 1 nanometer. That's what I want to convert this to. So that's why I have nanometer here. I need something equivalent in the bottom. So I'm going to put 1 times 10 to the minus 9 meters, because this one is the same as that one. This 10 to the minus 9 is the same as that n, and this meter is the same as that meter. So I know that this is equal to 1. And since I'm multiplying by 1, I'm not changing this amount. So when I do the work, I get 6.0 times 10 to the squared nanometers, which turns into 600 nanometers, just to give me an idea of where this belongs. And 600 nanometers puts us right there square in the middle of visible light? So my answer is this is visible light. Okay. All right. So what if it happened to be 800 nanometers? You'd say it's infrared. What if it happened to be 200 nanometers? You'd say it's ultraviolet. So hopefully, whatever number we get is going to be close to 400 or 700, and either in between 400 and 700, or slightly smaller than 400 or slightly larger than 700. And your answer is either going to be, for these types of questions, ultraviolet, visible, or infrared. All right. So we're done with this section. Thank you for listening. Try some problems in the back of the book.